Hook for today. Will a spinning merry-go-round pin spin longer with all the people in the middle or around the outside? And probably you haven't had a whole lot of experience with merry-go-rounds in your life because they were a health hazard. But when I grew up, we did a lot of tossing our cookies on merry-go-rounds because that's what fun was all about when I was growing up. Here's the same question again. That here all the children are standing in the middle, obviously having a good time, and the merry-go-round is spinning, and then the children all stand at the outside of the merry-go-round. I'm not sure if he's having a good time or not. And the question is, in which case will it be easiest to start the merry-go-round spinning? And once you get it spinning, in which case will it be hardest to stop? And so that's two questions with the same set of multiple choice in each. I look forward to seeing how you answered them. I hope what came out of your answers in the previous question was that the rotational inertia, which we represent with a capital I, depends upon the translational inertia, also known as mass, and how the mass is located. That if you put the children far away from the pivot, I hope you got the answer that there would be greater rotational inertia. And if you put the children the same mass but closer to the pivot, you have a lower rotational inertia, making it easier to cause accelerations. And so what we seem to have is that I, we're guessing, is proportional to m and perhaps inversely proportional to r. No, directly proportional to r as well. That larger r's mean larger i's and larger m's mean larger i's. It turns out that it's actually that the rotational inertia is proportional to mass, and it's proportional to the radius squared. For reasons you'll have to take AP Physics if you want to find out why. But this is to be memorized. The rotational inertia of a point mass is equal to its mass times its distance from the pivot squared. And if we have several point masses, like this problem, I'm going to treat this person as a point mass and this person as a point mass, then to get the total rotational inertia, you just add the rotational inertia of this person to the rotational inertia of that person. And in this particular case, we also have a merry-go-round, which has rotational inertia. The merry-go-round is definitely not a point mass. It's got bits of mass that are far away from the pivot and bits of mass that are up close to the pivot. And you would need to add all those up to find the rotational inertia of the merry-go-round. But fortunately, in this problem, you don't need to do that. That they tell you that the merry-go-round's rotational inertia is 100. And then you have these children to be treated as point masses, having this mass at that distance from the pivot and this mass at this distance from the pivot. And to get the total rotational inertia, you find out this rotational inertia, add on this rotational inertia, and then add on the rotational inertia of the merry-go-round. Notice the units. Units of mass times units of distance squared. Kilogram meter squared as units of rotational inertia. So if you would go ahead and finish that and get me a number. Now, this is the rotational inertia of a number of non-point mass objects. Here would be your merry-go-round treated as a disk. For a thin hoop, I hope you recognize that the rotational inertia looks just like the rotational inertia of a point mass, because after all, if you break this hoop into little masses, each one of them will be mr squared, and then if you add them all up, you'll end up with the total mass times r squared. That it's identical to having a single blob at a distance r away to having that blob spread out, but still all r away. When we get down here to the disk, or they call it a solid cylinder, I hope, although you couldn't predict that it would be 1/2 mr squared, I hope you can see that unlike the thin ring where all the mass is at r, here some of the mass is closer into the pivot. So we're not surprised that the rotational inertia here is less than the rotational inertia up there. For the sphere, which you will work with the sphere a lot, this is a solid sphere, they call it uniform, it's not a spherical shell. Again, some of the sphere's mass will be in closer to the pivot and some will be further away, and I hope you can agree that because it's not all in this kind of planar structure, but some of it comes up here on the sphere, that this ought to be less than this one if you take the total mass and shape it into a sphere instead of into a disk. If that's not obvious to you, don't worry about it, but these are values which you will be given at the top of the page, and you will just need to recognize that, oh, in this problem I'm dealing with a sphere, and so its rotational inertia is 2/5 the mass of the sphere times the radius of the sphere squared. For example, here is a problem where we are told that this rope is exerting a 15 Newton force. Here, we'll put it on here. And there's a cord and it's wrapped around this pulley. The pulley has a mass of 4 kilograms and a radius from here to here of 33 centimeters. And they tell us that the pulley accelerates. This is going to be rotational acceleration from omega I equals 0 to omega final equal 30 in 3 seconds. And oh, isn't that interesting? Okay, so we don't presume that the pulley is a disk where we could just do 1/2 mr squared. We don't know what to do with this pulley. We're trying to find the pulley's moment of inertia, but they throw in this extra thing that there is a frictional torque, that the axle here offers some friction, and as a result, I'm drawing this as a straight line, but I'm intending it to represent a torque that resists the rotation of the pulley. So your approach to such a problem would be to get at this rotational inertia you're trying to find by saying that the net torque is causing the rotational inertia times the net acceleration. That the net torque would be the sum of these two. You would have the torque from this 15 Newton force acting at an arm of 0.33, and then you'd have the frictional torque, which they gave us was 1.1. It is opposing the torque that is causing the acceleration, and then for acceleration I'll put in change in angular velocity divided by time. And they gave us all of that information, and so the only unknown here is I, and I'll ask you to write it down, but here it is calculated for you. And again, please note the units that you would have. What about if we treated this disk, this pulley, as a disk? Given the information they gave us here, that would be 1/2 mr squared, and the mass was given as 4 and the radius was given as 3. Oh, you can see we get a dramatically different result, that this is clearly not a disk. What if we treated it as a ring? Can you recall that formula? It was just like a point mass, which we have to memorize. Then it would be mr squared. We'd put in its mass and its radius. So this actual pulley in this problem lies someplace in between, being like a disk and like a ring. How curious is that? Not very curious. All right, now you try to work with this stuff. I've got a bike wheel. Here's its mass and its radius. There's a rope wrapped around the outside, and the rope is pulled with a constant force of 10 newtons. This is a good opportunity for me to talk about ropes around wheels. If you've got a wheel and you wrap a rope around it and you pull, I wrap the rope around it, rope around it, and then I pull on the rope, it will always be the case that if you have a flexible thing like a rope wrapped around a wheel, that the force will always act. I guess it should be pulling like that. Sorry. How can I get rid of that? I'll draw over it in white. No, be white. There, you see it went away. That the rope always acts perpendicular to the wheel. Always. And so when you take the arm crossed with the force, it'll always be 90 degrees between the two. If you were to try to not have it be perpendicular, suppose you tried to pull in that direction, then what would happen is this rope would unwrap from the wheel until this would be your force. Again, it would be tangent to the wheel, perpendicular to the radius. So it is the nature of a rope around a wheel that it will, when you pull on the rope, it will always act tangent to the wheel. That is a useful thing to know for the many problems you will be doing. Here you go. They've given you everything you need to know, and I would like you to calculate the torque. And as I have been intimating, you would use this formula to calculate the torque. And then we go on from that to get more interesting with the problem. Still the same force, the same radius, the same mass of wheel. What angular acceleration does this force of 10 newtons cause? And you now know the torque, so you should be able to get to the acceleration. And I pause a little bit so you can do it on your own, but if you have started the video again, I would suggest that this would be the formula. Here was torque as arm cross force, and here is torque as I alpha, because it's useful to me in this form now. And for I, I'm going to treat the bicycle wheel as a thin ring. So I put in mr squared for the rotational inertia, and then you can put in the values, and we've got everything we need from our solution for the torque in the first part to get the angular acceleration. And then finally we get to the real interesting question. If the wheel was initially at rest, how far will it turn in 3 seconds? And I'll give you a moment to think about what formula you would use, in fact, to go all the way to getting a solution. I hope you stopped the video for that sake, because it's good for you to practice using your head. And now we've started again, and you would use this formula to get to the question that they wanted, which was how far does it turn? What is delta theta? Oh, and we're done with the video. Congratulations!